Hello and good morning. Welcome to EBIO's first webinar in our series. This morning, we're going to hear from Robbie Venderbosch from the BTG Netherlands, and he's going to tell us about pyrolysis oil, about its production, challenges, developments, and how it's being used in real life. We'll be starting with Roman, who's going to give us an introduction to the project EBIO, and then he's going to introduce Robbie. So just a few housekeeping rules before we get started. If you have any questions, please use the question and answers box at the bottom of your screen, and do not use the chat box for a question because the chat box is just for chatting. So if you want to say hello and welcome to your peers or something, please use the chat box. Otherwise, if you have a question, please answer in there. The questions will either be answered by written or it will be answered at the end of the presentation verbally by Robbie or Roman. Okay, so I'd like at this point to hand over to Roman, who's going to give us an introduction to the project, and the floor is yours.
Thank you, Emma. Welcome, everyone. Let me just share the screen. I hope you see the presentation.
We see it and we hear you.
So again, everyone, welcome to the first webinar of the EBIO series. I give you a quick intro about the EBIO project itself. Basically, we convert industrial bioliquids using electrochemical methods and then evaluate how those upgraded bioliquids can be used for co-processing towards fuels and chemicals. In this project, we work a lot with the bioliquids themselves, but we also develop electrode materials, test them, optimize conditions, and then, as I said, the upgraded bioliquids we co-process under refinery operations. If you look at the value chain, then we, as bioliquids, use pyrolysis liquids, which is the topic of this webinar, and we also use black liquor. The electrochemical upgrading focuses mainly on the stabilization. So we want to convert, let's say, unstable groups into stable components, and also reduce the molecular size of those certain fractions. And then those upgraded bioliquids we co-process by FCC and by hydrotreatment to fuels or fuel precursors. In the series of those webinars, we basically go along this value chain. Today, starting with the fast pyrolysis, and then moving slowly towards the electrochemical conversion and the co-processing. So today's presenter is Robbie Venderbosch. He has worked at BTG, which is basically the world leader of fast pyrolysis technology. Robbie is, one can say, also the expert on pyrolysis liquids, and he will give us an update about the production, about the properties of those pyrolysis liquids, but also the routes for upgrading towards fuels and chemicals. So, Robbie, the floor is yours.
Thank you, Roman. I'll try to get my slides in front of you. Okay, here we are. You can see the slides, Emma?
Yes, now it's perfect in full screen. Yeah.
Let's go. Thank you, Roman, for this introduction. Welcome to everyone at this first seminar for EBIO. I took the topic on pyrolysis oil because this pyrolysis oil was one of the feedstocks we have aimed at in electrochemistry. With respect to the electrochemistry, you have to wait, let's say, 40 minutes or so to let me explain why we are using specifically pyrolysis oils for this very interesting purpose. My name is Robbie Venderbosch. I've been working for BTG now already 26 years or so. BTG is a company which is developing pyrolysis technologies, amongst others. We started in a broader field of biomass applications, biomass to energy applications. Right now we have about 25 to 30 people, FTEs, and the company is consisting of a consultancy company related to an R&D company. And what we basically do is knowing and trying to know everything about biomass conversion technologies. We have been focusing on the pyrolysis since 2003 or so, more in particular. And this also related to the, let's say, broadening the company in the sense of commercializing the technology for pyrolysis. This is on the left-hand side, this BTG bioliquids. But also now in the last couple of years in trying to bring this all into something better. And this is called BTG Next. Now, why I would like to show you this, this organogram of BTG. I'm there in the middle with the red box. I'm in the R&D department. We have a company called BTG Bioliquids. They are commercializing the company, but what is really relevant to know is that this is a separate entity. It's a separate company. It's a separate entity to commercialize the technology in particular. If you want to know anything about the R&D on pyrolysis or biomass, go to BTG. If you would like to buy a pyrolysis technology, to buy a pyrolysis unit, go to BTL, the BTG Bioliquids on the left-hand side. If you would like to know anything about hydrotreating and buy a hydrotreating unit, go to BTG Next, is on the right-hand side. I will show this picture later on to clarify a bit what the approach is. As said, we've been playing around with this biomass pyrolysis for the last 3 decades already. And to be honest, I'm in a very lucky position that I was there when we started, somewhere around the 1990s at the university. I was also the first one producing the oils for BTG at that time in 1992, if I remember rightly. On the right-hand side at the bottom, you see the first unit we have developed at the University of Twente. I was the one operating this machine. I was in a lucky position to be at BTG when we went into the TRL 5-6 level. We went into the bench scale, 200 kilogram per hour unit, which is now almost exactly 25 years ago. So we celebrated this part with a cake a couple of weeks ago, I have to say. The one is now shown on the right-hand side in the middle. I was lucky to be the operator, the designer, the maintenance guy at whatever on the unit in Malaysia. And in Malaysia, we built a 50 tons per day unit on empty fruit bunch. That one is shown here on the left corner in the top. And basically that was the successful BTG, but to be honest, also not completely a success for the client. So we decided to bring this one into a commercial arena and build the commercialization strategy around a new company called BTL. Because going from R&D into the commercial arena requires much more than only bringing the technology on the ground. It also has to deal with new organization, new commitment, new people, etc. The guys from BTL did a wonderful job in the last 15 years already. They built EBIO, which is a unit located here close to Enschede, here in Hengelo, in the Netherlands. And this unit has been constructed around 2014 and is in operation since that time. From this part, they also built 2 new units. Come to that part later. To show you a bit what pyrolysis is, it's not magic. What we do is we have biomass, and what we do is we heat the biomass with sand, and what we do is we evaporate the biomass and we condense the evaporated gases. You can see it here on the animation. You see this biomass particle. It's evaporating, producing the gas. These vapors are going into a cooling tower. That's where we condense the oil, where we condense the liquids from the biomass. And in essence, it's nothing more than condensing biomass and making a liquid biomass. And we do that with a pretty high yield. Since 2014, things speeded up a bit, especially in the area in 2019, 2020. BTL built a unit in Finland for Greenfuel Nordic. Basically, they built this unit on a greenfield. So they started with a completely empty field. The oil has been produced since then, has been used in combustion applications, and it was, from a technical point of view, above Pyro and Greenfuel Nordic, as well as the later one on Pyrocell, very successful. Pyrocell was built around 2020. It was in operation since 2021. Now, whereas Pyro as well as Greenfuel Nordic are using the oils for combustion applications, this Pyrocell is a new approach. Pyrocell is using the oils as a substitute for the fossil fuels in a refinery. So actually what they're doing as of date is to co-process these oils in an FCC unit. Now, what we essentially do in pyrolysis is we liquefy biomass and we solve logistics and we try to replace oil in a refinery. Give you a flavor on how these units have been built. BTL is highly involved in this construction of those units. A company very nearby, PTC Zeton, is involved in building the skids. The whole unit is built out around skids. And what you can see on the left-hand side is the construction of the unit in 2019. On the right-hand side, you really see the green field. Now, what's interesting about this is that although it will take a couple of months to build all the separate skids, the guys from BTL can build the unit within a couple of weeks. And in case of Greenfuel Nordic, the unit was already there without any additional items already finished, and it was built within 4 weeks from the skids delivered by Zeton. Pyrocell, I mentioned before, it's a very new and an innovative way of how we deal with these pyrolysis oils, changing of substituting part of the vacuum gas oil in an FCC refinery. So literally what they do is they replace 5%, roughly 5%, 3 to 5%, I have to say, of the vacuum gas oil, and they bring these oils into a final product which is close to the gasoline and diesel they typically get from an FCC refinery. The thing I always say about pyrolysis is that it has two very unique things. The one is it's not magic and we solve logistics. We have a lot of biomass available around the world, but it's always in a different structure, always in a very complicated structure. It always contains oxygen, and not only oxygen in the sense of the oxygen related to the carbon, so in the molecules of the material, but mainly the oxygen in form of air and then in the form of water. Besides, it's a solid material, so there is a problem with biomass. What we do is we get rid of the oxygen in the form of air, we get rid of the oxygen in the form of water, at least mainly, and what we basically do is we liquefy the biomass, we are able to pump it. We can do that, and that is surprisingly with a very high efficiency. And this very high efficiency is reflected here in this diagram below. In this case, the figures here are in megawatts. Megawatts of biomass for a typical unit from BTL is for a 5 tons an hour unit is 25 megawatt. And we are able to process these 25 megawatt inputs into an oil with more or less about 14.5, 15 megawatt of oil. So this is already a very high efficiency. Besides, we are also making steam and electricity. So it's not a loss. The real loss is only about 10-15%. So we are building units on biomass on small scale with a very high efficiency. So that's always the thing I really like about the biomass. For those who are interested to know a bit more about this and I'm not trying to give you to convince you. I would like to give you the arguments you can convince yourself. We have prepared a complete model of the pyrolysis units we have built for Pyro, and this has been literally placed on a website, and the website is given here below. And the website is providing you a freeware version of a simulating program, just like Aspen, slightly different, cheaper, because it's for free. You can download this from the internet. You can download the model on pyrolysis. You can really see what we are doing there in EBIO and why we get this high efficiency. That's the good part about pyrolysis. There is also a bad, and the bad part is that we have called it a pyrolysis oil, but honestly, it's not an oil. And this is a failure that has been made already in the 1980s, 1970s. These pyrolysis oils are not an oil, it's a liquid. And the phrase that we can do something in hours what nature does in millions of years, that's true, but not really. Because what we produce is not a very nice quality oil. What we do is we don't do the magic. We crack the molecules from biomass and we crack it into materials that does not resemble oil at all. And basically what it is, it's lignitic fragments of these of the biomass emulsified in an aqueous syrup solution. So pretty well, it's a syrup, it's a sugar, and the sugars are very reactive. This brings in a lot of R&D, of course. Now, why is this the case? Simply because biomass contains hemicellulose, cellulose, and lignin. And what we do is just crack those molecules. Again, it's not magic. And the hemicellulose are going into the acids and the carbonyls. The cellulose structures are basically the glucose molecules, and they end up like carbohydrates. Not the real nice sugars you would like to eat, but those sugars which are a bit dehydrated. They are both acids and sugars. They are soluble in water, and we produce lignins. Now, those lignins are very much like the aromatic stuff, and they are not soluble in water. So what happens is that this bio oil intrinsically is not stable. But the nice thing about these pyrolysis oil is because of the acids, we are able to make a one-phase oil. And why? Because those acids, they act as an emulsifier for the pyrolytic lignins. Besides those compounds, what we also do, especially with the cellulose structures, we are dehydrating the sugars. So we produce some water. Pyrolysis oil contains 20%, 25% of water. It contains about 5% of acids. It contains about the 20% of lignins we get from the lignin fraction, about 40% of the cellulose fraction, and it's all one phase. At least that's the purpose of the BDC technology, to make it a one phase. To give you some flavor about, let's say, the details, more like the details on these pyrolysis oil, water content around 20%. We don't destroy all the molecular compounds. The typical molecular weight is in between 200 and 2000 daltons. Gram per mole in this case. Should be daltons. The average is around 600 to 700. The elemental composition, it doesn't change that much compared to the original biomass. We just crack the biomass materials. We dehydrate a bit, so the oxygen content might be a bit lower than the original biomass. But basically the carbon, hydrogen, and oxygen are similar to the original biomass, and is also reflected then in the heating value, which is typically around 16 to 18%. What we do in pyrolysis is we are evaporating the gases. So that means that any kind of ash that would be there in the biomass will not be evaporated. And with the technology we have at BTG, the ash is not entrained in the gases, so the ash content could be very low. And typically we measure values of around 0.01%. So they are very low compared to the original biomass. The other thing is we have water content of around 20%, and that makes it pumpable. So the viscosity is typically 10 or 100 centistokes. It's easily pumpable. What we do on a regular basis here in the BDG laboratories is pumping this material from 1 bar to 200 bars in one step, for example. The other thing, what is important to know here, is this material is quite unstable. And the stability I always reflect in two parameters. And the first one is on the MCRT. So how much of this material will produce char if you start to heating it up. This is typically around 20%. Now, if you take glucose, for example, a nice glucose from your kitchen, if you start to heat up glucose, the MCRT value is also around 20%. So 20% of your glucose, if you start to distill this material in the nitrogen, will end up as char. The other stability index could be on the carbonyl. So how much of these carbonyl compounds, molecules are still there. If you look, for example, at sugar, one of the carbon molecules from the sugar contains the carbonyl function. The other ones, they contain the alcohol function. Now, in our case, it's more or less similar. The carbonyl is around 3 to 4 millimole per gram. What is now the thing about this carbonyl is that if you have sugars and you heat up sugars, they start to caramelize. If you heat up a material which is hydrogenated glucose, call it sorbitol in this case, then you can evaporate everything. Now, the essential thing is that these carbonyls are basically the most reactive part of your whole molecule. As I said before, it also contains acids, and especially the acetic acid, and the pH is typically in this 2.5, 3.5 region. As a matter of fact, I don't want to destroy, to remove the acids from, because as I said before, these acids also can be used as an emulsifier for the lignins in the syrup phase. The density of the material is pretty high. It's above the water. It's 1100, 1200 kilograms per cube. And why? Simply because it contains sugars. It still contains the sugar. To give you just some flavor about what these pyrolysis oils are, or pyrolysis liquids are, it contains water. And it contains 20% of water, but it also contains a lot of molecules that are soluble in water. So if we are able to, if you just add water to the pyrolysis oil, you start to phase separate the oil. You get the aqueous phase where you contain quite some water-soluble compounds, and you get a lignin phase. And this lignin phase is quite viscous. The water phase is really like water solution. It's easily pumpable, and that contains the sugars, it contains the alcohols, it contains the materials that has quite a high oxygen content. The water insolubles, on the other hand, they are the lignins. And those lignins can be diverted into two phases, which is basically the DCM solubles and the DCM insolubles. DCM solubles are the smaller aromatics. DCM insolubles are the larger insoluble materials. This material is a very complex mixture. You can see it already from this figure. It might contain over 250, 300 compounds. My impression about this oil is if you can identify a material, a component that contains more than 3 or 4 oxygen molecules, it will probably be there in the pyrolysis oil. To give you another idea about this material, so these water solubles are typically around 70 to 80%. Acids are there, it's 5 to 10%. Ether solubles, it will be there. The hexane solubles will be there. And you see there on the right hand side all kinds of molecules that might be very interesting to extract from the pyrolysis oil, but with very low concentrations. So bringing this material in a chemical compound and isolating all the chemical compounds out of this structure is very complex, very expensive, and it's not something that is easy to be done. So our strategy in the last 25 years was to look at this material and try to improve it in the sense that we would like to bring all kinds of biomass resources into that, literally here on the left-hand side, through a technology of pyrolysis, to a right-hand side where we have defined structures of molecules. You can use either for chemicals on the right-hand side as a functional group chemical, or the biofuels here in the middle, or on the right-hand side at the bottom, to use these materials as a co-refining option for gasification or for combustion. And as you can see from EBIO, the first 2 units we built, those units were specifically meant to be used as a combustion material to be combusted. So to bring these materials into a natural gas fired boiler or a fossil fuel derived boiler, replace part of the fossil fuels by biomass. We tried to get up into the ladder. So we went from combustion into co-refining. Co-refining is the part Prem is doing right now. Our topic is since 2001 at BDG itself is try to bring this material into a biofuel. And to bring this into a biofuel, we have to play around with the oxygen. And I explicitly say play around It's not like removing the oxygen directly. No, to find smarter ways how we can bring this oxygen into a better functionality. That's how I would like to explain. I hope it will be clearer in a couple of slides. My personal interest since 2001 was on this hydrotreatment. And this hydrotreatment is essentially nothing more than adding the hydrogen into the molecule, like what you do with glucose and sorbitol. Bring glucose into sorbitol. Glucose is not distillable, sorbitol is. I can do that with hydrotreatment, with hydrogen, but an option there is to produce this hydrogen through electrochemical means. It's a very interesting method. We can buy an electrolyzer. We did. We recently built an electrolyzer and used the hydrogen from this electrolyzer into our hydrotreatment units. What you also can do is try to use this electrochemical processing directly on the biooils. So not to convert these protons into hydrogen, use this hydrogen over catalytic means into the biooil, but use the protons directly in an electrochemical cell to upgrade your biooils. I'll come to that part later. Let me explain to you first on the hydrotreating of the pyrolysis. It was a concept we have been looking at since 2001. And what the principal idea was we have hydrogen, we have pyrolysis oil, we bring it into a reactor with a certain catalyst, we bring temperature in, we bring pressure in, and we produce gas, oil, and water. And now the problem sets in. It is not an oil. It is a sugar. And a sugar requires something different than just a catalyst you can use for typical oils. And I try to explain that into a Van Crevelen plot, and that is shown here on the bottom. It's a bit of a complicated picture to see just like that, but what it shows a trajectory going from pyrolysis oil into gasoline, which is not a straight line. It's not a straight line. No, what happens is if we increase pressure, temperature with the right catalyst, we first start to do some hydrogenation at a rather low temperature. And at a certain temperature, at a certain condition of the pyrolysis oils, those pyrolysis oils start to behave differently. Like in glucose to sorbitol, you start to produce a lot of alcohols. Those alcohols start to dehydrate, so the line of repolymerization and the thermal dehydration. And only when you have passed that point, typically around 250 degrees Celsius, you start to add hydrogen to your molecule and really to deoxygenate the material. And this plot typically shows you how smart nature is. The pyrolysis oil is a combination of sugars. Sugars are very reactive. You have to transform those sugars at low temperatures. Combined with lignins. Lignins, they behave a bit like oils, and you have to treat those lignins at high temperatures. And in between, you can make advantage of the fact that you can produce alcohols and start to do the dehydration. I try to explain that one in another plot, which is shown here. So we start on the left bottom. I hope you can see my cursor here. We start here with the pyrolysis oil. We would like to do the hydrogenation, and this is sugar chemistry. We just would like to add hydrogen to the molecule. We don't want to destroy the oxygen per se there. We would like to defunctionalize the oxygen, try to bring those aldehydes into an alcohol form. Once you do that, the alcohol becomes reactive at 250 degrees plus. We go down in the ladder here, in this S-curve. You start to produce water. You start to produce all kinds of alkanes and stuff like that. And at a certain temperature, 250 degrees plus, or 300 degrees Celsius, you start to produce, or to get those hydrogen reacting with your components and start to deoxygenate your materials. So what we have done in our 25 years of experience in hydrotreating pyrolysis oil is trying to find out the best way to do this. Sugar chemistry first, taking advantage of the alcohol chemistry, and then at a later stage to the lignin chemistry. They all require different temperatures, different catalysts. Sugar chemistry typically is on rainy nickel kinds of materials, low temperatures, high pressures. Lignin or oil chemistry, typically NEMOs, COMOs, conventional oil chemistry, rather low pressures of around 80 or 100 bars, but high temperatures. Completely different system. What I have shown you here on the left-hand side is the reasoning why we did it like this. It shows you the pyrolysis oil in a small syringe, and this pyrolysis oil is typically black. Once we start to do the hydrogenation at low temperatures with a specific catalyst, we were able to bring this black material into a reddish type transparent oil, this hydrogenated liquid. This has nothing to do with the oxygen content. For both, it's around 30-35%, but you really see the color change. And exactly this figure made me change the looks at pyrolysis in itself. The process we would like to bring into a commercial field has been derived on basis of this knowledge. We don't want to do the deoxygenation completely at 400 degrees Celsius directly. No, we would like to bring the oil slowly to a state where we can use NEMO's COMOS catalyst. And we do this through an intermediate step called stabilization. And the stabilization is basically reflecting the sugar chemistry we need to apply anyhow. So what we do there is we add hydrogen to the molecules. We have developed a technology, we developed a catalyst for this, which is typically operating at around 200 degrees Celsius, high pressure, and this catalyst we refer to as a picola. The picola catalyst is completely different than any type of catalyst you use in the oil chemistry. It's based on a nickel and a copper. It's prepared in a different way, and it's really active in hydrogenating the aldehyde from the pyrolysis oil. You might ask yourself the question, why 150 bars? Well, the answer is quite simple. Hydrogen is not soluble in water. And we need to have some sort of high hydrogen concentration in the oil to get the reaction being done and to get the selectivity for the aldehydes into the alcohol. Once we have done that, once we have prepared those stabilized materials, we can start to play around with the water content. We can evaporate part of the water. We get the, let's say, the sorbitol-like structures. They are much more stable. Typically, MCRT values of around 20% for pyrolysis oil are reduced down to about 7% for the stabilized oils. And from these stabilized oils is well, I won't say a piece of cake, but it's much easier to go into the full deoxygenation mode. In the stabilization step, we need hydrogen, of course. And in the stabilization step, we need around 100 to 250 liters of hydrogen per kilogram. That sounds reasonably high, but this hydrogen is not wasted. It's added to your molecules. So essentially what we do in the stabilization step is bringing the aldehydes into the alcohols, and we don't lose hydrogen. In this full deoxygenation step, we start to dehydrate the material. We lose the hydrogen in the form of water. Besides that, we are also at a temperature where we start to produce some carbonaceous gases, methane, ethane, and stuff like that. So we lose quite some hydrogen in the next step. We have done this development in a couple of projects before. We started in BioCoop in 2006. We had a couple of projects together with Syntef on this topic, fast card for refinery and waste to road. They have been ended in 2019, 2020, 2021. And now we have a couple of new projects ongoing in this aspect, which is the called Revolution and Fuel Up. Revolution is mainly to bring these oils into a co-refining mode. So can we bring those stabilized oils into an FCC unit and do it even better than when we do it with the pyrolysis oil? This Fuel Up is recently started, January 2024, and the Fuel Up is meant to produce materials pure from the pyrolysis oil. So bringing this pyrolysis oil, deoxygenated pyrolysis oil, completely down to fuels for marine and kerosenes for the aviation industry. Some setups we are using here at the laboratory. We are using 5 continuous hydrotreaters, and they are rather small ones. It's shown here in the middle. It's around 60 to 100 grams per hour of oil, what we use there. We have 5 of those units in continuous operation 24/7. We have a larger unit here on the left-hand side. and this is typically around 2 or 3 kilograms per hour, so 50 liters, 50 kilograms per day. And those units are, let's say, the larger ones with typical volumes of around 3 to 4 liters in a reactor set. On this 50 kilograms per day unit, we have recently installed the electrolyzer, so we are now using green hydrogen to produce those liquids. What we can do, what we can make, is fast pyrolysis oil. What we can make is everything in between, going from fast pyrolysis oil into fully deoxygenated oil. Now, what we also do is we sell those products. So we sell fast pyrolysis oil. You can go to the web shop related to the website of BTO, where you can order those flash pyrolysis from this fast pyrolysis oil. What is not on the web shop yet, I have to say, is that we also can sell materials in between those fast pyrolysis oil and the complete deoxygenated materials. And this is a whole series of compounds we have defined as stabilized oils, stabilized deoxygenated oils, and fully hydrotreated pyrolysis oil. Just contact me if you are interested to receive samples. By the way, they are not for free. It will cost a lot of money to prepare them, so they are not very cheap. To give you some idea about what the fuel properties are, and you can see it from the left-hand side to the middle. You go from water content of around 25% down to water contents less than 0.1% for a fully deoxygenated oil. If you go for a stabilized oil, you get values of around 10%. Density really goes down, and the LHV value, the heating value, really goes up. The acid number, we really destroyed the acid at that time. They really are destroyed. The acids are gone. What is really important here to know is that this MCOT value, so the charring tendency of this material, really goes down from around 15 down to 1% or so. This is typically what we would like to do in a company called BTG-Net. You saw that on the right-hand side in the organogram. And what we are trying to build, what we're trying to make more tangible in the next couple of years, is to have a unit available specifically for this purpose. Why are we doing this? Essentially because we would like to bring this oil into a refinery mode. And there are a couple of options available, of course. First of all, we can bring this pyrolysis oil and bring it into an FCC unit and replace the vacuum gas oil directly. This is being done by Frame, but the problem with this is you cannot do that unlimitedly. So you have to be limited. This is limited to around 3 to 5%. And a maximum would be around 5 to 10%, because what you are injecting in your whole refinery is a sugar phase. What we can do with the stabilization is trying to get rid of the sugar phase and try to produce alcohol. And then it sounds very reasonable to bring this co-feed ratio up to 20, maybe 30, maybe even higher percentages. That's what we have to see in the next couple of years. And this is typically what a revolution is about. We also can bring this oil into a material where we don't have any oxygen anymore. And this is typically what we are doing in Fuel Lab. We are doing some the lab and pilot testing. We get a really high comfort level that this is possible. And there are very nice opportunities to do this together with refineries. And this concept, this strategy is shown here on the right-hand side. Either you bring in the pyrolysis oil to the refinery or the SPO or slightly modified version, or you make more or less a drop-in fuel called the HPO, which doesn't contain any oxygen anymore. So this is a revolution where we have this approach on co-refining, and the co-refining option has been seen specifically in terms of the fluid catalytic cracking mode of a refinery. So we are trying to change the substitution ratio to try to substitute the vacuum gas oil and increase the substitution ratio. And a revolution here is specifically designed around the idea that we have to make the standards for these co-treated materials. Fuel Up Fuel up is where we have to produce the fully hydrotreated rollers oil, distill it, and make the complete pure marine and aviation fuel. Those are both projects. Revolution started in 2023, Fuel Up in 2024, for which you will see some results being generated in a couple of next years. What's interesting, I showed you one before, is that this oil is not an oil, it's a liquid, it's a lignin, it's a sugar phase, it's a syrup in which the lignins are emulsified. That makes it quite straightforward to separate the oils. Why are we not separating the oils in the water-soluble part and the water-insoluble part? Because both have different functionalities, both have potentially different applications. And that's exactly what we do at BDG as well. We build a very large demo plant to fractionate these oils into pyrolytic lignins and pyrolytic sugars. Also, these materials can be bought at BDG, by the way. So just contact me, and we can make you an offer to send you some of these materials. What is interesting about the functionalities of these materials is that the lignins are the aromatic, the sugars are the carbohydrates, but they have specific means in different applications. And to show you a bit what they are, those pyrolytic lignins, they contain much more, the pyrolytic sugars, they contain much more water because we have added water to the pyrolysis oil, and the pyrolytic lignins just less water because they are not soluble in water. But as you can see from this table, you can see there's huge difference in the qualities and the properties of these two phases. Lignins are very viscous, for example. The pyrolytic sugars are watery. We can evaporate part of the water, of course. Some things are alike, some things are completely different. But what's interesting to see is that from these materials you can make different products. So the sugars are pretty good feedstock to prepare all kinds of polyols. Right? You can bring those glucose type of materials, carbohydrate materials, into the polyols. The polyols are not the very clean polyols we would like to have right now. That's a matter of time, I hope. But these polyols can be used for different manufacturing lines. And this is done in a project called New Wave. And New Wave is aimed at 4 manufacturing lines for which we can use the different fragments of the pyrolysis oil. Basically, the wood panels, furan-based chemicals, the polyols, and the engineering wood. And especially this engineering wood would be a very interesting option as well, because those aromatics basically already have this type of functionality to help a wood material against all kinds of fungi. That brings me all this stuff into what we can do with electrochemistry. EBIO is about electrochemistry, and we were in the lucky position that we were able to bring pyrolysis oil into an electrochemical project. And to explain you a bit what electrochemistry is, a very simple setup. We have water. Water can be split into oxygen and hydrogen. That's a very simple process. But actually, it's not a very simple process. Water is one of the most stable molecules you see on Earth. That's also the reason why we have a lot of them. But to bring water into hydrogen and oxygen, pure oxygen and hydrogen, it requires a very massive force. I don't think there's any technology that can do that at 20 degrees Celsius 1 bar, except for an electrolyzer. So that means that in an electrolyzer, you have a tremendous force on your water to destruct your water into oxygen and hydrogen. That means that if you can bring this force into different chemicals, you will have an extra degree of freedom to play around with to bring materials into a preferred product. And that's exactly what we did with electrochemistry on pyrolysis oil. Because what I want to do in pyrolysis oil, I would like to make them more stable. I would like to get the oils more stable, not necessarily in this sequence, but I would like to make these oils more stable by lowering the aldehyde content. That's what I did with the hydrogenation. I would like to bring sugars into alcohols. What I also would like to do is to bring those lignins, these lignitic materials with a very high molecular weight, bring them down into a more reasonable area. It was the typical average size is about 2000 or so, 1500, 2000. I would like to bring them down to around 1000. The last thing I would like to do is to try to remove part of the acids. And the acids, I know these acids are also relevant in stabilizing the emulsion. So it's not a very straightforward one. But all these options can be done over electrochemistry. And that's the interesting thing. For example, on the cathode side, I can easily reduce sugars, and these sugars can be transformed into alcohol. And there was a process already in the 1930s, and it's referred to as the Creighton process. It has been vanished, evaporated from the literature a bit, but those sugars can be hydrogenated into the alcohols, into the sorbitol, and this was the first process to do so. And then came the catalytic process, and the Creighton process was gone. So I'm able, principally, to bring those sugars into the alcohols. And if I go to the anode side, there's a lot of literature available on depolymerization of the lignins. So we should be able to depolymerize lignins, especially over nickel-based catalysts, and make them smaller. The other thing that happens on the oxidation side, as a process already invented in the 1800s, probably it was the first application on the electrochemistry on acids, was the Kolbenhoven-Muth decarboxylation. So to couple the methanes from the acids, make ethane, and they decarboxylate the acid. So basically oxidizing acids to prepare hydrocarbons. All this together led me in 4 years ago to go for EBIO. So on the anode side, try to remove the acids, and on the cathode side, try to use the protons from the decarboxylation to hydrogenate my sugar molecule. And this is a very interesting concept. I can do it at 20 degrees Celsius, 1 bar, and so far it looks pretty well. The old concept could be a bit like this. I take the oxygenated prolozol, I do the electrolysis, I stabilize my oils, I get rid of the acids a bit, I hydrogenate my sugar a lot, and from this I go into the hydrodeoxygenation and I make my middle distillates, SAF, my kerosene, gasoline, etc. So this was the original idea about EBIO. We had to change, of course, concept a bit, because prolozol are not very straightforward molecule feedstocks for electrochemistry. So we tried to make it a bit simpler and try to do it in with a phase separation in between, because those sugars can be easily extracted from the prolozol. Those lignins should go into the oxidation phase. We can separate them separately. So this is more or less the concept what we do right now. We have the prolozol from fast pyrolysis, we separate them, especially the carbohydrate phase we bring into the reduction side of the cell. And on the oxidation side, we bring in the lignins. So we use the protons and electrons from the lignins to reduce the compounds in the sugar phase and make a better material at the end and start to do the further refining. This is a picture I've taken yesterday. What we do is not literally yet what I explained on the sheet before, because on the oxidation side, I started to use water. So on the left-hand side, you really see water where we do the water oxidation, how we produce oxygen. There are options to do it slightly different. But on the right-hand side is my main strategy right now, is to use prolozol derivatives and do the reduction of this material and try to bring all those protons and electrons in my molecule. This has not been switched on yesterday. It has been switched on 2 weeks ago. And it has been running since then. So this has been running already about 14 days or so. And to my surprise, without any problems. Now, to my surprise, also, I can measure the amount of hydrogen. And the amount of hydrogen is basically what I lose as protons and electrons. And what I can see here, that's about 80% of my protons and electrons are going into my molecule. I know the challenge up front, which is basically analysis. So how do I define that the material we produce from this is better than the protozoo? So that will be the next step for us here at BDC. What is another option to go for electrochemistry? And that's a bit outside the scope of EBIO, but I think it might be interesting to explain here as well. That's my last couple of slides. In the arena of fast pyrolysis, we are producing char, we are producing the oil, but we also are producing some non-condensable gases. These non-condensable gases are basically hydrogen, CO2, CO, and methane. If I'm able to combust all these gases with oxygen, I'm able to produce water and complete pure CO2. And what would be very interesting if I can use excess of electricity from my pyrolysis process to bring the CO2 into fuel components. So use something like a power to liquid strategy. So that means sequestrating CO2 and bring that one into a format I can add into fuel components, preferably to be added to my flash pyrolysis. And this is exactly what we would like to do in the next 5 to 10 years, I would say. Use oxygen from the process of electrochemistry, make the pure CO2, and bring this pure CO2, first of all, in formic acid, but then go a bit of a step beyond. Go from this formic acid into products that can be added as such to my flash pyrolysis, and it's here rephrased as formose reaction. Going from formic acid into formaldehyde to the formose, go into the formose products, bring this formose products in my flash pyrolysis. And why is this of interest? Because these formose products appear to be similar products as what we already have in our flash pyrolysis. So it's a nice and very unique concept. I've shown you this slide at the beginning, and it's also the slide I would like to end with. I'm here at the beginning and in the middle. I'm here at a company called BDG. Now you might understand why we have separated this whole biomass technology holding BV at the top into BDG R&D, that's where I am, into BDG Bioliquid on the right-hand side for commercialization, but also BDG Next, which is basically the company that will be handling commercialization of the upgrading of products. I would like to thank you for your attention. I can accept a couple of questions from your side. Before doing so, as you noted already, there are a couple of projects, quite a lot of projects we have been doing together with the European Commission and a lot of partners involved. And they are, of course, they are acknowledged for this concept. Thank you very much.
Thank you, Robbie. That was really interesting. A lot of information there, lots of projects as well. So great. We have quite a lot of questions. Some of them have already been answered by Romans whilst you've been speaking. We have got time for a few questions. So let's start with this first one here. Do you know how efficient the complex treated pyrolysis process is in comparison to the HCl process? You have a comparison of efficiency.
Yeah, enough of efficiency. Yeah, I know. Yes. I'm always surprised to see that HCl has a very high efficiency in potential. If you take the data from the past, and I've been diving quite deep into this concept in let's say 10, 15 years ago. The carbon, I always relate to carbon efficiency. I think that's fair. And carbon efficiency into liquid materials. So that's the restriction. But if I look at pyrolysis, then you will end up with around 60-65% of the carbon from your biomass that ends up in liquids. If you take it for HTL, potentially you go to 80-85%. It goes into a liquid. But this liquid is not a liquid. It's more like a solid kind of structure. It's a very high molecular weight. So the material is not alike. They are different. But the potential is there to go to very high carbon yields going from biomass into the final product, liquid solid. So that's a very interesting part. The downside is that if you want to bring biomass into a high pressure arena, for me, it's a no-go. After 25 years, it's a no-go because solid are not easily pumpable. And that's the real difference between HTL and pyrolysis. The complication you have on pressurizing the material in HTL compared to the low pressure at pyrolysis makes it a very complex and thus rather expensive type of technology for the time being. But there might be changes there.
I'm sure there will be in the future. Thank you for that, Robbie. There is a lot of questions here. I think we have time for another two. So I pitched this one, and then maybe Roman, you'd like to pick the next one. So Robbie, do you have any projects or plans to tackle the isolation or purification of the aromatic chemicals, such as glycol or the DCM solubles?
Well, those aromatics, they always contain some oxygen. And we do have quite some projects. We did quite some projects in the field of lignin chemistry. If I take the example of lignin chemistry, lignin is a very interesting material, but you should handle it nicely. So the lignin from pyrolysis oils, if you derive the lignin, you extract the lignins from the pyrolysis, is a very nice material to start with, although it has a very high molecular weight. But if you know the concepts of lignin and how to treat it, I think there are very nice ways how to bring these lignins into better materials. I think in about 1 week or so from now, we have a PhD defense of a guy. He used to work with lignins, and he did that one in the arena of ABC salt. ABC salt, I have to say it in English. And this ABC salt was bringing these lignins into fuels. And the interesting thing there, I can share you already, is that we have, I'm never lying, I've never seen so high carbon yield going from a feedstock into a final fuel as what we have achieved in ABC salt. 80% plus overall, the overall process chain, 80% plus.
Good. So, excellent.
Yeah. So this lignin is very interesting material.
Great. Thank you for that answer. And then I'll just hand over to Roman for the final question. And then there are quite a few, so we'll work through them, and maybe Robbie or Roman will send you emails with your responses afterwards. But hand over to Roman for the last one.
There are a few questions related to the impact or the effect of the biomass quality or composition on the bio oil composition.
Huge. Well, I never believed in a one solution for all. But also in the case of pyrolysis, there is no one solution for all. What we can do is you can make a liquid out of anything. But so even with very bad materials, you can make a liquid out of this bad material. The problem is that in a further application, the liquid properties will be completely different. Now, in general, what you see is the more ash you have in your biomass, the less your yield will be and the more water you produce. But besides, the more complicated it will be to use these liquids as a further product for upgrading, for example. And there's what really happens in between, what really happens in the pyrolysis because of the ash is still a bit uncertain. But ash, especially ash, is I think one of the crucial parameters in your original biomass feedstock to determine the quality of your final product and application related to that. So with respect to impact, the question on impact, this is the highest impact, especially the ash content has the highest impact on yield and quality.
Thanks again, Robbie. I think there's just so much to cover in this topic. But an hour is just not enough, especially reflecting with the amount of questions we've had and the amount of participants. So I just want to wrap up this short webinar. Say thank you very much. Please follow the website, EBIO website, for more information on the EBIO project. Of course, there's the BTG website, which has got more information on all the other projects that Robbie mentioned. And the next webinar in the EBIO series will be held on the 7th of May at 10 a.m. in the morning. And it's about the electrolysis part of the project. So here we are. So the link's in the chat box if you want to register now. Okay, so thanks again for your participation and hope to see you at the next webinar. Thank you.
Thanks, everyone. Bye.
Thank you. Bye.